I will show some more daring projects that can be calculated with this project. This is a project which is under construction actually in United Kingdom. So they are building a glass bridge, or we can say a glass swimming pool, in between two buildings. So it's a quite complex shape, and it's quite complex to calculate it by hand. And it's a daring project, but it's under construction actually. You can find a lot on YouTube. So I took some information from the internet regarding the thickness of the elements and made a model in SIA. It's a shell model. As I described, we need to model glass with shell elements. And there is the hydrostatic pressure of the water. So we apply water pressure, but also we generated the wind using the 3D wind modulator, 3D wind modeler from SIA Engineer. And we performed a third order analysis with large deflections. So we see exactly the correct distribution of forces. If we resume only to linear analysis, then we have higher stresses than in reality. So glass, it is expensive, but still we need to limit a bit the cost. So we need to calculate, if it's possible, closer to the real behavior, of course going through the partial safety factor. So it's a non-linear analysis performed by SIA engine. SIA has a very fast FEM analysis engine. It's developed by FEM Consulting. I think it's shared with Drupal. They have the same solver. So it will bring a different solution from linear and non-linear analysis. Usually non-linear geometrical analysis, we have higher deflections but smaller stresses. And we can see here, have a look on the displacements. Maybe they look a bit strange. They are due to the wind that I have applied sideways. And it's like an envelope of the biggest deflections. And also we can see here the stress distribution in each finite element on the deformed shape. So again, this although it's a single layer shell, I use the effective thickness calculated with that converter that I presented before. So that converter offered me the solution to know what is the effective thickness. And then I can do the unity check. So aside from looking at the stresses and thinking of myself opening an Excel and determining the capacity, we can just use the functionality in the software to determine the capacity based on our additional input. So this is a table of forces that can be included in the engineering report. And now we are performing this stress check. So we see a unity check of 0.73, which translates in 73 usage of the glass. And we see at the bottom where we have the biggest deflection and the biggest tensions. And again, if we switch to detailed report, we'll know exactly. Here we have a lot of stories because they are multiple. There are 10 layers of glass used. In case one breaks, the other will take over. And this is how it's calculated. And this is a validation if the model is good for stress analysis or for deflection analysis. And usually we have to perform both. And also this is the allowable deflection determined by the software according to the norms.